In today's module, we will look at inferential statistics. Till now, we have covered basics of statistics and descriptive statistics. In inferential statistics, these are the 5 sub-modules we will see. We will see the basis and the need of inferential statistics. We will see how we use inferential statistics in estimating the mean of a population. Then there is a concept of t-scores. If you remember, in descriptive statistics, we have seen a concept of z-scores. Now in inferential statistics, we use t-scores. Then we are going to move on to see what are the correlative and predictive techniques used in inferential statistics, and finally, types of study and hierarchy of evidence in inferential statistics. So let's start with the first module, that is basis of inferential statistics. Let me start with a very basic question. Why do we need inferential statistics? Now you have to understand that when you are given a set of data, yes, you want to represent that data, understand that data, but a more important function in statistics is how we can use that particular set of data, draw inferences which can be generalized to the entire population or to a subset of population. For example, suppose there is a drug for hypertension. Now you cannot test that drug on all possible patients. So you should be able to take the data of test results on a group of that drug on a group of patients, and you should be able to use the results, that what kind of results can I expect by using this drug in patients to a population in general. So that is the need of inferential statistics. Now the basis of inferential statistics is a theorem called central limit theorem. What is central limit theorem? Central limit theorem actually states random sampling distribution means will always tend to be normal irrespective of the shape of the distribution from which it is drawn. Again, I'll try to repeat and let's see if we understand. Random sampling distribution means will always tend to be normal irrespective of the shape of population distribution from what it is drawn. Now I know what you will be thinking. You will be thinking, what the F does it mean? So let's see an example, the best way to learn. Let's start. We have a pack of 100 cards and each has a number from 0 to 99, right? So there are 100 cards. First will have 0, second will have 1, third will have 2. So similarly, there are 100 cards, each has a number from 0 to 99. If we plot the frequency distribution curve of our cards, we will have a curve like this. So each of the number will be having frequency 1, because there is one card of 0, one card of 99 and one card of any number in between. Now what we do is we take a pack of 5 cards out of it and calculate the mean and plot the mean which we get. So suppose we get, so there is 100 cards, we pick randomly 5 cards and we add the numbers given on the card and take out the mean. So let's say the first card is 2 plus 3 plus 4 plus 5 plus 6. So we add whatever card number we have got and we just take out the mean. And if we plot a graph of that mean, this is what we are going to get. So this is the frequency and this is the mean of the random sample. So 5 cards we are picking. So it's a randomly 5 cards we are picking. We are adding and calculating the mean, and this is the frequency curve. Now this is what the central limit theorem, that irrespective of the frequency curve of the original data set, if you take the mean random samples, you are going to get a binomial or a normal distribution curve. So essentially this is because this we have learned in descriptive statistics, that if we have a normal distribution curve for anything, we can use it for a lot of statistical calculations. So this here in this case it's a linear straight line. It can be a linear progressive line, it can be a zigzag frequency distribution curve, original distribution curve. But if you take a mean, if you take a sample, this mean of random samples will always have a distribution, normal distribution curve. So I hope this explains you a little about central limit theorem. We are going to use the central limit theorem in actual, so you will learn more about it. So this is what exactly. The most important part is the mean of the random sampling distribution of the mean is equal to the mean of the population. So if you have a random distribution, so the mean of this curve is equal to the mean of this curve. So even if you don't know the mean of this curve, in actuality, if you have got a mean of random samples and you know the mean of that, you can be very sure that this mean and this mean is same. I know it's a little confusing at this stage, but let's see the application and you will understand more. So there is something called standard error of mean. Now, when you distribute, if you remember any distribution curve, you used to have standard deviation. Now, standard deviation in case of means of random sample is called as standard error of mean. Standard error of mean is nothing but a standard deviation divided by the sample size under root. So this is the mean of the sample. So you know the standard deviation of the means and you know the sample size. So you can calculate the standard error of mean. Now, it is very important at this point to realize that standard error is inversely proportional to the square root of the sample size and thus forms the basis of the fact that studies with larger sample size are more trusted. So suppose the sample size is, let's say, very large. So this entire thing, so if this is the denominator is very large, this value will be becoming close to 0 as it is becoming large and large. So for a larger study, study with a huge sample size, the standard error of mean will be very, very low. So that's why studies with larger sample size are trusted more. There is something called estimated standard error. So estimated standard error, we know that standard error of mean or standard error calculation requires the knowledge of a mean of a population or a very large number of sample to get the curve. So if you have to, like in our original examples, we drew a pack of 5 cards out of 100 and we plotted the mean. So we have to do it enough number of times. We have to take this particular random sampling enough number of times to get that binomial distribution curve. If the sample size is very, very less, we may not get the exact binomial distribution curve. Now in that case, there is a statistical measure that is called estimated standard error, which is used as opposed to the standard error of mean, which we saw in the last slide. Now, so estimated standard error is nothing but standard deviation root under n. We will see again where S is standard deviation. So if we use estimated standard error, there's a tool called T table or the T score which is used. So T score is very similar to Z score. The only difference is Z score you use in descriptive statistics, where you know the data for the entire sample size for the entire population, where T scores is used in inferential statistics, where the number of sample is very less as compared to the entire population. Now we are going to look at both of these, estimated standard error of error and its application and use of T table in upcoming slides. In this part, we are going to learn about inferential statistics. The second part, estimating the mean of a population. Now, you realize that once we have given a data of a sample, we want to use the data from the sample to extrapolate it to the population. That's the entire basis of inferential statistics. Now, before we get into that, there is a concept of confidence limits, and we have to understand it, because since you are using the sample to a data from a sample or a set of samples to extrapolate it to a population, it cannot be 100% accurate. So the confidence limit determines how accurate your estimation is. So you can have a 50% confidence level, you can have a 95% confidence level, you can have a 99% confidence level. So mean plus minus a standard error of mean defines the confidence level, which means you take the mean of the sample plus minus one standard error of mean is equivalent to 68% of confidence level. Mean plus minus 2 standard error of mean is equivalent to 95.45% of confidence interval. Mean plus minus 3 standard error of mean is equal to 99% of confidence level. Mean plus minus 1.96 standard error of mean is equal to 95% of confidence interval. Now, in medical, the most important and the most frequently used is 95% of confidence intervals, which is mean equal to plus minus 1.96 standard error of mean. I'll explain you further this concept by taking an example. Let's say that the mean pulse rate of a random sample population is 76 per minute. So what happens is you go out, you pick a random population, and you just take the mean of the sample. I mean, you pick 5 or 10 people or whatever people, and you measure their pulse rate, and it comes to be 76 per minute. The standard error of mean is 4. So 60, and the standard error of mean, your calculation is 4. So 68% of the observation will remain between 72 to 80. So based on the first observation, you can say that 68% of the observation will be between 72 to 80 per minute. 95% of the observation will be 68 to 84. So it's nothing but the mean plus minus the standard error of mean according to the observations. So which also means another way to look at it, alternatively, if we measure the pulse of a person, then there is a 95% chance that the pulse rate will be between 68 to 84 per minute, right? So this exactly is confidence limits. Now this confidence limit, you will come across all research papers everywhere when it comes to statistics, that how confident you are of your results. So let's look at another example. So this is something which again you have to learn. Right? You have to understand another important thing which I want to tell you here is, since standard error of mean we have seen is inversely proportional to the square root of the sample size. So to reduce the confidence limit by half, you have to increase the sample size by 4. So if you have to reduce the difference, so here the difference is 68 to 84. If you want to be more accurate, then you have to increase the sample size by 4. Now let's look at another criteria, that is precision and accuracy. Precision is nothing but it's the degree to which a figure, or such as an estimate of a population mean, is free from random variation. So precision is this. So width of the confidence interval represents the precision. So the more precise, the lesser the width of the confidence interval, the more precise the information, the data is, and the lesser the width, more precise the figure is. Accuracy is degree to which an estimate is immune from systemic error or bias. So the more accurate it is less biased result. I know it's a little confusing, so let me try to explain you by a diagram. Now it's a dart board, and we are just throwing darts at the dart board. Now these are the 4 things which we have, 4 darts. Now this is unbiased but imprecise, which means there is no systemic bias. All the darts are not towards one place, but they are imprecise. I mean, they are not very precise. They are very widely distributed. Here they are very narrowly distributed, but they are biased towards one particular corner. So this is a precise information, precise observation, but this is biased. This is imprecise and biased. I mean, even there is a huge difference between each observation, I mean each dart, and also they are towards one particular area. So it's a bias, so inaccurate and imprecise. Now if you see the last, here everything is within a small range, so it's a precise, and since it's in center, so it's an unbiased or accurate result. So I hope this diagram helps you understand the difference between precision and accuracy. Another way to look at it would be these curves. I mean, I know it's just look these curves one by one. Let's look at the curve D, right? So D, if you see, just look, D and A both has the same mean, but D has a shorter confidence limit, if you see, and it is very the mean of D is actually close to the mean of the population. So D is an accurate as well as precise estimate. If you see A, so it is accurate because it's towards the center. It's accurate and but it is imprecise. If you see the width is a little large than the D. So it is accurate because the mean is very similar to the actual mean, but it is imprecise. I mean, width is very high. Let's look at curve B. Curve B is biased. I mean, it is not precise. It's not an accurate, because accurate, the mean, this is the mean of the B and this is the actual mean. So this is an inaccurate observation, but it is precise observation because the curve is, very, very narrow. If we see the graph C, it is both inaccurate because the mean is not coinciding, or it's very away from the actual mean, and it is also imprecise because it has worst of both the worlds. It's an imprecise and inaccurate observation curve. So I hope with this curve, both these curves can be used to create image based questions. In this module, we will look at t-scores, the concepts of t-scores. Now you have to understand that t-score is very similar to z-score. Z-score is used mostly in descriptive statistics when you have a complete or near complete set of data, and t-scores is used in inferential statistics where you have a data of a very small sample size, and then you want to use the observations from that particular data and extrapolate it to the entire population. Now, the use of let's again estimated standard error. Now, as I've already explained, that a standard error of mean or a standard error calculation requires the knowledge of the mean of the population, again, which requires large number of samples to get the curve, which is not clinically possible when you are doing a test of a drug. You cannot have very large number of samples being drawn. So in such a situation, what we have is called estimated standard error, which is standard deviation divided by the square root of the sample size. So if standard error is what we use a table, t-table or t-score instead of z-score or z-table. Now t-score and z-score are very similar. If you remember the formula of z-score, it's almost similar to what it is, but just in front of standard error or standard deviation, we use standard error of mean. So SXA. Now, understanding standard t-table. So this is what a t-table looks like. So there are few things I like to highlight in a t-table. So first thing you will see is area in two tails. So there is typically a two-tail test and a one-tail test when you are doing t-scores. So area in two-tail, so it will have 0.1, so 10% confidence interval, 5%, so 95% confidence interval. So this will be there. Area on one-tail, so 50%, 0.25 and 0.05. This is the 95% confidence interval which we generally use in medical for one-tail test, and this is the 95% confidence interval which we generally use in medical in two-tail test. I'll come to both one-tail and two-tail test in a short while. Then there is a column for degree of freedom, DF. So this is degree of freedom, and then these are the observations. So these are the three things which you have to understand. There is something called area in two tails. This is the diagram. Area in one tail. This is the diagram, and degrees of freedom. Let's move forward. We'll come to the t-table in a short while with an example. So degrees of freedom is n-1, where n is the sample size. So when we are looking at the t-table and we want to understand what is the degree of freedom we have to look at, we just take the sample size and minus it by 1. So as n becomes very, very large, t-table values very close correspond to z-table. Now this is very important to remember. I told you we are using t-tables because sample size is low. If the sample size becomes very, very large, even if we use t-tables, the value will correspond as if we are using a z-table. So z-table is for descriptive statistics, T table is for inferential statistics, and even though you are using T tables, but the data set or the sample size is very large, T table values become very corresponding to Z table tables. Now, what is this 2 tail test and 1 tail test? Now, if you create a hypothesis which has greater than or less than, it's a 1 tail test. So something like if you want to test what percentage of the population will have pulse less than 68, pulse more than 95, such kind of test where less than or greater than is used, it is called as 1 tail test. When a hypothesis has plus minus sign, then it is a 2 tail test. So what percent of population will have a mean pulse of 72 plus minus 6? So this is a 2 tail test. So hope you understand, because we will see it with an example also of a 2 tail test. Now, as I told, let's move to an example. A random sample of 15 people has a mean heart rate of 75 beats per minute with a standard deviation of 8.2. What is the range of heartbeat of 95% of the population? Now, this is the beauty of, this example will demonstrate the beauty of inferential statistics. I told you, you went on a street, you picked up 15 people, you took their mean heart rate, and it came out to be 74 beats per minute. Since you have the individual observation, you can calculate the standard deviation, and in that case the standard deviation is 8.2. so now you want to know that what would be the normal values of the heart rate of the population, that is 95% of the population. What can we say that 95% of the population, what is the range of the heartbeat for 95% of the population? Now let's look. Given 74 beats per minute, that's the mean. Standard deviation of the sample is 8.2 and sample size is 15. So from the these are the things which are given. So let's just start. Now we will be using estimated error of mean, because we have taken just one sample and of 15 people and we have just one standard deviation. Suppose we have taken thousands of samples and each with a different sample size and each with a different standard deviation, then we could have used standard error of mean. But since we just have taken one sample, here we are using estimated error of mean. I hope you understand at this stage why we are using estimated error of mean and not standard error of mean. They are very similar, but one is used when the number of samples taken is very high, one is used when the number of samples is taken very low. So in this case, only one sample we have taken, that sample size is 15. So we are using estimated standard error of mean. Now if we see the calculation, so this is the calculation. We have standard error of mean is nothing but standard deviation divided by root of the sample size. So 8.2 divided by under root 15, which comes to 2.1. So standard error of mean in this case would be 2.1. Degrees of freedom, since we have the sample size which is 15, n is 15, so degrees of freedom will be 15 minus 1, 14. Now let's look at the T table. I hope you at this stage we are going to T table. Now this is a 2-tail test, because if you see what will the 95% of, what is the range for 95% of the population of the heartbeat of the 95% of the population. So we are not talking about what percent will have more than this or what percent will have less than this. We are just talking about what percent, what is the value for 95% of the population. So it's more about plus minus situation. So it's a 2-tail test. So let's see. Since we are looking at 95% confidence level, so this is the 95% confidence level for a 2-tail test. If it was a 1-tail test, we would have looked at this column, right? Because in 1-tail test, 95% confidence level is this, right? But since it's a 2-tail test, we will look at this value. So this is the column we took, and degree of freedom we calculated is 14. So where they intersect, this is the value which we get by looking on the T table, that is 2.145. Let's move forward. So we have mean 74, stated error of mean 2.1, and T value for 95% confidence interval from the table is 2.145. So 95% of the observation will lie between mean plus minus estimated standard of error of mean into T value. So 74 plus minus 2.1, we have calculated standard error of mean, and t value which we have looked from the table. So 74 plus minus 4.5, that is 69.5 to 78.5. So we have taken a sample of just 15 people, and based on that observation we can say that 95% of the population will have a pulse or a heart rate of 69.5 to 78.5. So this is how we use inferential statistics.